I'll start recording. And I'm going to assume the material from section 1.2, that's mathematical induction. You've used it in linear algebra. And we're actually not going to use it today. Although today would be a place to use it, but I think we just don't have enough time to fully prove everything that we're supposed to prove today. So I will give hints of the proofs and refer you to the book for the full proofs. So just so we're clear, we're going to define if we have a function f which maps between a and b. We're going to call it bijection if it is so injective, which is the same as 1-to-1, and surjective, which is the same as onto. Hopefully that's a familiar definition. And now our topic for today is finite and infinite sets. So we're going to start out with the really boring definition. This is just to show you how we can define these really basic things from what we've assumed. And what we've assumed is some basic set theory. Okay. Okay, so first we're going to define what it means for a set to have n elements, which is kind of silly, but okay. The set S has n elements if there is a bijection between S and 1 through n. Okay, hopefully that's pretty clear. The idea being that you can use that bijection just to count the elements of S, 1 through n. This right here is one of the reasons that I would like to have 0 in our set of natural numbers, but again, I'm going to try to follow the book until it drives me absolutely crazy. And
excuse me, but
yeah.
Wouldn't that be the set of whole numbers, since whole numbers are essentially natural numbers with 0?
Yeah, some people use that term. Yep. Yeah, I mean, everybody has their, every mathematician has their preference for whether 0 is a natural number.
Can you clarify what n equals 0 means in this definition?
Yeah, good point. So the book actually makes a distinction here. I don't think it's necessary. So if n equals 0, what do we want? We want a bijection f between S and the set 1, 2, and this would be our notation, right? 1, 2, up to 0. Okay? And there's no number that fits in there. There's no number between 1 and 0. So what we do is we interpret that as being the empty set. Okay? So if n equals 0, we want a bijection to the empty set. Okay, and actually, think about it. There's only one set that's going to have that bijection. It's going to be the empty set. Okay, no other set could be injective. Oh, no other set could have that. Okay, I see the reason for why the book is being careful. But anyway, only the empty set is going to have that bijection. For no other set could we even define a function to the empty set. Because in our definition of function, we said that it had to associate to every point in the domain a point in the range. Okay? So if our range is the empty set, we just can't define any functions at all from S to the empty set unless S itself is the empty set. Okay? So that's what it means to have n elements. And, these definitions, I want you to see them so you know that we're building everything from base principles. The whole course, we're going to build everything from base principles. We're not actually going to use this. We're not actually going to go down to this definition. Okay? B. Okay. The set S is finite if it has n elements for some value of S, some value of n. Okay, so the first definition defined what it means to have n elements. The second one is what it means to be finite. And the third one is what it means to be infinite. And we're just going to take the easy way out here. Oops. The easy way out is to, if you can spell it correctly, is to say that it's infinite if it's not finite. Okay. Those are just the very basic definitions. We have a theorem then. Well, yeah, I guess we'll call it a theorem. And that's that the cardinality of a set, the number of elements in the set, can only be one thing. So we're going to call this the uniqueness theorem. If S is finite, then S has n elements for only one value of little n. Okay. So I would hope you'd look at this theorem and you'd say, well, that's obvious, right? And it really should be obvious. The reason you would prove this theorem is to double check that our definition of the number of elements in a set actually captures the notion that we want it to. Okay, that's the only reason you would ever prove this theorem, is to check that the definition above was correct. Okay. Now, let's go through the proof. So we have to use our definition that we set up right here. Okay. There's a few lessons from the proof. Let's say, suppose that S has m elements and n elements. Okay. Now I want to make a general mathematical point here. This might sound like a proof by contradiction to you, but you do not need to write it as a proof by contradiction, okay? What I'm going to do is at the end of the proof, I'm going to conclude that those two numbers are the same, and therefore it can only have that number of elements, okay? Then by the definition, oops, I just saw somebody asked in chat if I could scroll up a bit. I'm going to scroll up to the definition here in a second. So there are bijections. F from S to, and let's call it G okay, those are our bijections, and that's just using this definition of what it means to have n elements. There is a bijection from the set to that 1, 2 up to n. Okay. Now, these are both going kind of the wrong, well, they're both, here's S, we've got G mapping it into 1, 2, n, and we've got F mapping it into 1, 2, m. Okay. What I actually want to do is I want to look at, what about the inverse here? F inverse maps 1, 2 up to m into S. Okay, so now we're using something about functions that technically we haven't proved, but it's not hard to prove, and if you've seen it before, it's obvious. Injections have inverses, and the inverse of an injection is an injection. Okay, so thus there is an injection F inverse from set 1 through m into S. And now we're going to use the fact that if we compose injections, oh sorry, I said injection, I meant bijection. So let me fix that real quick. Yeah. Now we're going to use the fact that if we compose bijections, we get another bijection. I guess we'll use hence. There is a bijection. Now, we want it to map from, I'll write down what we want it to map from and to first. Okay, if I want this bijection to go from 1, 2 up to m into 1, 2 up to n, then I want to start down here, follow F inverse, and then follow G, and end up here. Okay, so we just have to remember our convention for that, and that's that we do F inverse first, and then follow it with G. Okay, so that is our bijection from 1, 2 up to m to 1, 2 up to n. And now we basically just remove that set S. We don't care about it. And now what we need to argue, and here again it comes down to how much are you going to assume and how much you're going to reprove. is that you can only have this bijection if m and n are the same. Okay, and
That makes sense.
so, because G composed with F inverse is injective. Okay, it's injective, it's 1-to-1. That means that we have to have different images for each element of the domain. So n has to be at least m. Because G composed with F inverse is surjective, so every element of the range has to be mapped to. That means that we need the number of things in the domain to be at least the number of things in the range. Therefore, m equals n as desired. And that's the end of the proof. Okay, so let me pause here if there are any questions about the proof or...
I'm still a little confused on how G composite F inverse is injective or surjective.
Yeah, okay, so when we were up here, so we assumed that the inverse of a bijection is a bijection. Okay? I mean, assumed is maybe the wrong word. We knew that it was true. So I'm assuming that we've seen that. We agree that that's true.
For our conclusion,
Mm-hmm.
can we use the definition of the amount of elements in a set and say that since we have this bijection, we know that this first set has n elements, and then that would make them have the same amount?
So I guess you're right. We kind of didn't write like a final punchline.
Mm-hmm.
So I've shown that m equals n. If we go back up to this top of the proof, we said that let's assume that it has m elements and n elements. So if it were to have two different cardinalities somehow, there would be some m that's different from n.
Mm-hmm.
And then we've shown that won't happen, because any time that it has m elements and n elements, then m equals n. So I guess what I'm saying is at least for me, this is a sufficient conclusion to say, yeah, we really proved the theorem. Okay.
Okay, thank you.
And like I said, I mean, I want to expose you to this so that we see that everything is built up from simple things by proofs. But this is not the level we're really going to be focusing on, because if you go back and you prove all of this stuff, then it just takes so long. It takes too long to get anywhere. Okay. So, I mean, from now on, you're allowed to assume that if you have a finite set, then yes, it has a number of elements, and that number of elements is somehow unique because we just proved it. Okay.
Makes sense.
Thank you. So, again, oops, we'll call this a theorem. The set n is infinite. And again, here's where we get into this. If we prove everything, we're going to run out of time, and we're never going to get anywhere. So, what does this mean? This means, according to our definition, infinite just means not finite. Okay? So, finite meant there was a bijection, right? There was this bijection from your set into 1 through n. So what are we claiming here? That means that there is no bijection from the natural numbers into 1, 2, up to n. Okay. Now,
it's a bit confusing to me. Isn't 1, 2 up to n? Oh, it's not the entire natural numbers. Okay.
For any, yeah. So we should probably put a quantifier in here.
Okay. Cool.
Okay. So then how would we prove this? Well, our proof would look at, there's a lot of ways to prove this, but one thing I would want to look at is this set. There must be a repeated element in there because that's n plus 1 images. Okay. You know, it gets a little bit annoying proving things, that mathematical things at this level, because you kind of have to say, well, wait, what am I allowed to assume? If you're asking me to prove this, then because this is so basic, what am I really allowed to assume? But I hope we agree that this should be a proof. Oh, I had the question in the chat. Would that be enough for a quiz? Yeah, certainly. I think that was about the conclusion to the last theorem.
A question.
Yes.
So, would we ever be asked to prove something on a quiz that we didn't fully do in class? Kind of like these ones, like you're saying, if we proved everything, that we would be here all day. But is there anything that we would ever have to prove that we didn't fully go over in class?
Once we get into the more difficult material, I think it'll be clearer. Obviously, this course isn't about finite and infinite sets, so that's one reason why we're going through this so quickly. Okay, I'll try and I'll try and make it really clear before the first quiz what we want, and we're also going to have a homework that's due a week from today, so you'll get a sense on that. But both the homework and the quiz will be mostly proofs, so prepare for that. Okay. So this is all we're going to say about finite and infinite sets. Okay, the existence of these bijections, and then we're going to move on to different types of infinite sets. So we're going to have a definition here. And people differ on this definition too. I'll just warn you. So the set S is denumerable if there is a bijection. F from the natural numbers into S. Okay, we're gonna define this to be denumerable. You'll find other definitions of these terms elsewhere. The set S is countable if, okay, countable means we can count its elements 1, 2, 3, 4, 5, etc. Except we're also saying we can count the natural numbers because we can just keep going forever. So we're allowing ourselves to count forever. So it's countable if it is finite or denumerable. Okay. Now, there are all kinds of, so instead of denumerable, some people like to say countably infinite. And then some people actually take that denumerable to be countable, and then they have to say things like finite or countable. Anyways, just for this course, we're going to take it to be denumerable means you have to be infinite and have this bijection with n. And countable means either finite or denumerable. So a comment in the chat was these ifs. I guess they really are if and only ifs because they're in a definition. Okay? You can interpret them as if and only ifs. Final definition to go with these. The set S is uncountable if it is, not countable. Okay, let's just do a couple examples. Are we doing on time? Well, we got 15 minutes. We'll do a couple examples. One, the even natural numbers are, they're definitely not finite, but they are denumerable. How do we show that? Well, we have to find our bijection. So our bijection is supposed to go from the natural numbers to our set. So how do we map the natural numbers into the even natural numbers? Oops. And the natural numbers go on forever. And so do the even natural numbers. Okay. Well, there's a really easy way. We just map 1 to 2, 2 to 4, 3 to 6, etc. So if we just define f of n to be 2n, this is a bijection from n to, the set of even positive integers. Oops, that was enough to show that they are denumerable. Okay, any questions on that example?
Not specific.
Hello, so this is me after the lecture. What happened was that the recording of the whiteboard accidentally got stopped partway through, most of the way through. But I still have the whiteboard, I think. There we are. I still have the whiteboard. And so what I'm going to do for the rest of this recording is just go over a little bit what we talked about after the recording got stopped. Okay, so our next example was, so let me just go back to the even integers here. To the integers. We talked about how really the easiest way is just to list the images of the natural numbers, 1, 2, 3, etc. And as long as you put them in a list and you get everything in that list precisely once, then your set is denumerable. And that's really kind of what it means to be denumerable. So we did another example. We did the set of ordered pairs, n cross n. Okay, now there's a lot here. I'm just going to go over it fairly quickly in this extra recording, and you can look in the book for more details. But we we did a thing called diagonalization. So we put every ordered pair at its position in the Cartesian coordinates, and then we went down in diagonals. So our first diagonal just had 1, 1, and then our second diagonal had 1, 2, and 2, 1, and then 1, 3, 2, 2, and 3, 1, and so on and so forth. And so this way we are going to get every single element of this ordered pair in one of these diagonals, and our list is going to associate to each ordered pair what natural number maps to it. Now again, this is not a function we really want to write down. Okay, now the next example we did, we want to go from this to the rationals. So I will scroll up to that. Okay, so we said first, let's focus on the positive rationals. And we said we can write them in the same kind of planar setup as before. And then we can use a diagonalization argument. And now we can get every one of these rational numbers in our list. Except the problem is, numbers such as, say, 1, well, let's just look at the ones. The ones occur infinitely often. And in fact, every fraction will occur infinitely often. Here's another 2 over here. That 4 over 2 is another 2. So then we said, well, okay, let's just say we're going to cross out all of the fractions in our table that are not in their lowest terms. So we're going to cross out 2 over 2, 3 over 3, 4 over 2, etc. Just leave them off the list. And that's enough to show that the positive rationals are denumerable. Okay. Now, yes, our list will look like 1 over 1, 1 over 2, 2 over 1. Now, what about all of the rationals? Well, if the positive rationals are denumerable, then the negative rationals are denumerable too. Okay? Just put negative signs out in front of the positive rationals and use your same list. Okay. So now what can we do for all the rationals? Well, we interleave the positives and the negatives. So maybe the evens map to the positives and the odds map to the negatives or something. And that gets all the rational numbers except for 0, and 0 we can just toss that in at the beginning. So now our bijection that we're thinking of would map 1 to 0, map 2 to 1 over 1, 1. It would map 3 to negative 1 over 1, negative 1. It would map 4 to 1 over 2, and 5 to negative 1 over 2, etc. So the rational numbers are denumerable. Okay? Now, this down here is nothing to worry about. That came up in answer to a question. The main theorem that we did not get a chance to prove in class was that the real numbers are uncountable. There's no way to put the real numbers in such a list. We're going to get to this. I think we're going to come back to this in our coverage of Chapter 2. Okay, so this concludes my summary of what happened in class after the record button got turned off accidentally.